All right, we've just come out of the sections in section 5.1 and 5.2 where we learned about the Riemann sum. And in this section, we're going to transition to what some might call shortcuts. Shortcuts for computing definite integrals. And this shortcut requires something called the fundamental theorem of calculus. And there are two parts to it, and we will, in this video, focus on the fundamental theorem of calculus part 2. Okay, so you'll recall that we know what the definite integral is, the definite integral from a to b of f of x dx. And we know that that means to compute a Riemann sum, a limit as n goes to infinity of the underestimate, or that will also be equal to the limit as n goes to infinity of an overestimate of a sum of rectangles, of the areas of rectangles. And this has the interpretation of an exact area under the curve f of x. So long as that function is positive, this function can be interpreted as area on the interval I from a to b. Okay, and we know that little s sub n is the summation. Let's say that the functions are such that if you do the left endpoint approximation, that I will go from 0 to n minus 1, the function a plus I delta x multiplied by delta x, or an overestimate oftentimes found from the right endpoints or the left endpoint, depending on the nature of the function, right? That this will be also a sum I going from 1 to n f of a plus I delta x times delta x, I going from 1 to n. Okay, now I suppose what I should, just for clarity here, maybe we should say not ascribe those to over or underestimates, because we don't know anything really about this function. So I should perhaps be a little bit more careful and say that I can say that this is the left endpoint approximation and this is the right endpoint approximation. And depending on the function, this could be capital Sn or little sn for the sum. So this is where we have come from. Okay, and what we're going to do now is to try to compute this definite integral not using its limit definition. Okay, now there is an interesting result in this section called the fundamental theorem of calculus part 2, and then we can say we can extend this chain of ideas. So here's the definition. Okay, here's how do you compute it. You compute number 1, you can compute number 2, and here is the meaning of what it is that you've computed. But there is a third method of computation, compute number 3, and that is using something called the fundamental theorem of calculus part 2. And the fundamental theorem of calculus part 2 says that if you want to find the definite integral from a to b, being the area under the curve, you need to just find an antiderivative of the function. An antiderivative of the function that you are finding the definite integral of. And then evaluate that at the top limit b and the bottom limit a, which means that you just need to find an antiderivative at the two endpoints and subtract them. Okay? So we have seen in a prior video, we went through all the Riemann sums to do the definite integral from 0 to 4 of 16 minus x squared dx, and we found from the Riemann sum definition of that we got 42.667 or 128 over 3 as the answer. So here, let's revisit this example using the fundamental theorem of calculus. So all you need to do is to take this function that you were finding the area under. You need to find an antiderivative of it, just an antiderivative, not the most general, but just any antiderivative that you can find. So that would be 16x minus 1/3 x cubed. There is an antiderivative. Then you will evaluate the function at 0, evaluate the function, the antiderivative function at 4, and that will give you 0. It will give you 64 minus 4 cubed. 4 times 4, 64 over 3, which is 128 over 3. Okay, so now that you found f of 4 and f of 0, the fundamental theorem of calculus says that you need to subtract those, f of 4 minus f of 0, which is 128 over 3 minus 0, otherwise known as 128 over 3, which is what we got from the Riemann sum. So this is just been a short video on how to use the fundamental theorem of calculus part 2 and putting that into the context of the limit definition of the definite integral.